Let me give you a little bit more details about the MCT ABC test methodology. Why are we doing it and how do we do it? Like Greg said earlier, the few crashes that are happening in Arizona and California are not helping with the public confidence and public trust. We fully believe that AV can make ground mobility safer, cleaner, and more equitable. In the meantime, without the public trust and confidence, their full potential may not be realized as soon as they could. So let's look at the systematic way of designing AV and win public confidence and trust. Let's imagine the whole possible driving out there that someone needs to solve is this big red rectangle. Some may argue that this big rectangle is infinitely large and fuzzy because there are so many possible combinations. In the meantime, let me first introduce this concept of Operational Design Domain, also known as ODD. When we deploy the Level 4 shuttles in North Campus of the University of Michigan, we limit the speed to be 12 miles per hour. We don't operate in snow, and it has a fixed route. When the deployment of AV is geofenced, speed limited, weather limited, they have a well-defined ODD. So the ODD is this big red rectangle. So the job of the designers is to make sure that a bigger and bigger area of the red rectangle is shown to be safe. In the meantime, the job of the evaluators or verification validation guys or V&V guys are trying to show that a bigger and bigger portion of the red rectangle is known to be safe. These two functions are usually done by two different groups within a company, or the V&V function can be done by the government or a trusted third party. So how do we do the V&V part? We are proposing this MCT ABC test concept. ABC has two meanings. Number one, we first think that this is a first step toward a systematic definition and methodology for V&V. Second, A actually stands for accelerated evaluation. Safety events are rare events. We know that there is only one fatal crash every 100 million miles and one police reported crash every 500,000 miles. Obviously, we don't have time to drive so many miles. Therefore, we have to do the evaluation in an accelerated fashion. B stands for behavior competence. We have built a library of 50 scenarios, and we obviously understand that not all 50 scenarios should be tested for every AV. In fact, the scenarios and test cases should be selected based on the ODD of the AV. Finally, corner cases, we must find a systematic way of testing at the boundary. In other words, cover the corner cases. We talked to many of the MCT members. We have 60 industrial members. In addition, we talked to researchers all around the world, including Asan Sakura Project from Japan and Pegasus from Germany. We also work with a lot of researchers and read their papers all around the world. And most importantly, we compare notes about how naturalistic driving data look like. Obviously, the driving culture, behavior in China, Europe, and US are all very different. But after accumulating a lot of driving data and we compare our notes, we found that while the detailed parameters behavior may be slightly different, qualitatively they are all very similar. So here's a little bit more detail of how we cover the big red rectangle. Now the details is shown in this green ellipse. Out of all the real-world driving, we carve out the real-world driving into many blue ellipses, and only those blue ellipses falling within the ODD will be selected for testing. Our primary job is then to select the test case parameters so that the red ellipses are approaching those blue ellipses as much as we can, in other words, covering all the way to the boundary. And when we choose the test case parameters, we must ensure that they are done in an accelerated fashion and cover the corner cases. So the more detail of how we sample from those test case parameters are the following. Here are 4 example scenarios: pedestrian crossing, cutting, unprotected left turn, and car following. In short, we cover a lot of naturalistic driving data. We build models, and we try to sample test case parameters from the model. The color in the last row of the table show how challenging the test cases are. Green means easy, yellow means medium, orange means hard. The red color shows impossible cases. Obviously, it's meaningless to test impossible to avoid cases in a test facility because we know the result is a crash. So today we are going to demonstrate 7 scenarios as examples for the MCT ABC demo. So we'll be using the 3 test vehicles highlighted on the left-hand side, and the 7 scenarios are selected based on several considerations. Number 1, they are all from our 50 scenario library. Secondly, they contribute a lot to the challenging crashes, and human-driven statistics show that they are very important. And thirdly, we are using them to show that we can test even the more challenging test scenarios that are not easily to test. For example, for door opening, we are developing technologies that leverage the MCT OS and the automatic testing functions that we have developed in order to show that we can do testing that many other places are not yet ready to do. So please enjoy our demo of these 7 scenarios.
In this example test loop, an ABC test car will encounter 7 different scenarios in a single loop. This test loop consists of 1. A highway merge. 2. A highway cut-in. 3. An opening door. 4. A deer in the road. 5. A crossing pedestrian. 6. An unprotected left turn. And 7. A roundabout merge. The test loop begins with the highway merge. The test car approaches the highway on an entry ramp. The challenge car remains in the right-hand lane, preventing the test car from immediately merging. A successful test would involve the test vehicle slowing down or coming to a smooth stop before safely merging, preventing the test vehicle from hitting the challenge vehicle. In the second scenario, the highway cut-in, the challenge vehicle approaches the test vehicle from the left and abruptly cuts in front of the test vehicle. A successful test would involve quickly slowing the test vehicle down to avoid hitting the challenge vehicle. Next, for the opening door test, the test vehicle approaches a stationary challenge vehicle from the left. The challenge vehicle's door opens abruptly into the test vehicle's path. A successful test would involve the test vehicle successfully swerving to avoid hitting the open door of the challenge vehicle. The fourth challenge places an obstruction in the form of a deer on a blind curve on the right-hand side of the road, directly in the path of the test vehicle. A successful test would involve the test vehicle slowing down and proceeding cautiously. For the next scenario, the crossing pedestrian, a mobile robotic platform representing a pedestrian abruptly moves onto the street into the path of the test vehicle. A successful test would involve bringing the test vehicle to a smooth stop, preventing the test vehicle from hitting the pedestrian. In the sixth scenario, the unprotected left turn, the test vehicle approaches an intersection. From the opposite direction, the challenge vehicle makes a left turn directly into the path of the test vehicle. A successful test would involve bringing the test vehicle to a smooth stop, preventing the test vehicle from hitting the challenge vehicle. For the final challenge, the roundabout merge, the test vehicle enters a roundabout. As it circles around, The challenge vehicle enters the roundabout, merging suddenly in front of the test vehicle. A successful test would involve the test vehicle slowing down or coming to a smooth stop, allowing the challenge vehicle to safely merge and preventing the test vehicle from hitting the challenge vehicle.